Good morning, everyone. Today we're going to continue our lecture from last week. And if you remember, last week we introduced the pressure projection method, which essentially was a way to solve for the primitive form of the Navier-Stokes equations. So if you remember, we said that the Navier-Stokes equations, they contain four unknowns, four equations. So you have U, V, W, and a pressure, and four equations. So the system should be well posed. However, we didn't have an explicit equation for the pressure. So we ended up doing the vorticity-streamfunction formulation that got rid of the pressure, essentially taking the curl of the Navier-Stokes equations to eliminate the pressure. But then saw that there are limitations with that approach. Going to 3D makes it really complicated. It's hard to do complex boundary conditions, complex geometries, because how do you define the stream function? You have to figure out how to set up the vorticity. Boundary conditions, really complicated. We really want to solve the equations in primitive form, because then boundary conditions are natural. You set up boundary conditions on the mass flow rate or on the velocities directly and or on the pressure. But there was no equation for the pressure, and last time we described a strategy to obtain an equation for the pressure. Now, compared to the vorticity-stream function, formulation, the primitive variable formulation, or the projection method, is really nothing more than taking the divergence of the momentum equation. So in the stream function vorticity formulation, we took the curl of the Navier-Stokes equations to eliminate grad P. For the primitive form, we take the divergence of the Navier-Stokes equations to get an equation for the pressure. So if you put div in front, if you take the divergence of the momentum equations, that's going to give you a del squared P for the pressure. You move everything to the left-hand side, you solve for the pressure, and you update. But then we came up with this fractional step algorithm that essentially says, first, solve the equations for a provisional velocity field U tilde with the right-hand side excluding the pressure. So this includes the advective terms of the momentum equations, and this includes the stress tensor or the diffusive terms. And we wrote it as A and D because you may choose to do the conservation form or the non-conservation form, whatever you like. But what doesn't exist here is the pressure, because we don't know what it is. Now, the idea here is that this U tilde is not necessarily divergence-free. It's just a velocity field that results from solving an advection diffusion equation. There's no constraint for it to be divergence-free. Then we said, OK, we're going to use the pressure to correct U tilde in a way to produce a velocity field that is divergence-free. And we showed the Helmholtz decomposition that mathematically enables us to do this decomposition. And the way we write this is say un plus 1, which is our true velocity field that we want to be divergence-free. So we want div un plus 1 to be 0, minus the provisional velocity field over delta t equal grad p. And then take the divergence of this. So once we take the divergence, we know this is a condition. We want div un plus 1 to be 0, so we set that to 0. That leaves us with div U tilde. Remember, U tilde is not divergence-free, so this is non-zero, equals minus del squared P. So that gives us an equation for the pressure. Del squared P is div U tilde over delta T. U tilde is obtained from this guy. Once we find the pressure, then we take it and put it back here to get a un plus 1. And this should guarantee us that div un plus 1 is 0. Can we double check? Yes, of course. So we have un plus 1 minus U tilde equals minus delta t grad P, right? Grad P. And we have del squared P equal div U tilde over delta t, right? So now the question is, div un plus 1 equals 0? So essentially, if we solve this and then solve this for the pressure, because we know this guy, the question is to find P. So this is a system of linear equations. You've done this in the past, and we did it kind of in the second lecture of class when we were doing the steady state heat equation in 1D. So we know how to solve this. It's just a boundary value problem. We know how to solve this for the pressure. So you solve for the pressure, you put it in here. my claim is that when you put it in here, then un plus 1 is div un plus 1 is 0. So is div un plus 1 0? Let's check. We know un plus 1 is u tilde minus delta t grad p. So div un plus 1 is div u tilde minus delta t del squared p is equal to div u tilde minus delta t. What is del squared p? Div u tilde over delta t, which is equal to 0 indeed. Okay? So this process converts u tilde into a divergence-free velocity field. Helmholtz decomposition. Okay? Great. So now I'm going to exit, and I mentioned something about boundary conditions. Essentially, one way, it's a big, there's a lot of literature. It's a big world out there for boundary conditions. One of the simplest ways to think about boundary conditions here in this case is to think of u as a correction to u tilde, or u tilde as a correction to u. Okay, and then say at the physical boundaries, if we know u, we don't need a correction. Okay, so then the correction, then both u and u tilde are equal. Sorry. So the way to think about this is to say that grad p is a correction to u tilde to make u divergence free. But if you know u, then you don't need a correction. Therefore, u and u tilde are equal at the boundaries. So if you know u at the boundary, you just set u tilde equals to u at the boundary. And that also implies a Newman equals 0 boundary condition on the pressure. Okay? Because when you substitute here, if you don't need, if u equal u tilde dot n, so the normal velocities, then dp dn equal to 0. So that gives you Newman conditions on the pressure everywhere. Okay? Now, this is not the most general, but these boundary conditions do really well. Did you have a question? No. Okay. So now I'm going to switch back. Must set a value. Yeah. Okay. So yeah, you should know this from your PDEs. So with Newman boundary conditions and a Poisson equation, you need to at least fix one value. Otherwise, you're not going to get a unique solution. But for iterative solvers, this is not an issue. Anyway, let's not worry about this now. I'm going to go back to the Navier-Stokes implementation. We started implementing this last week, if you remember. It was called in class finite difference Navier-Stokes. Okay. I messed up my Jupyter installation on my other computer. I was trying to take data from here and put it in VTK for visualization. Can you guys see? Okay, maybe if next time you can scoot a little bit closer so that, whatever works for you. Okay. So I want you to open up this notebook that we started putting together last week. I'm going to go through it really quickly, at least what we did last time. Okay. So import the boilerplate stuff. And then we decided to do the central differencing in x and y and the Laplacian and the divergence, put them all into functions because that simplifies the implementation. Okay. So if you want me to remind you of the discretization, it was just basic finite difference discretization. Okay. Here. Convective fluxes, just essentially central on the convective flux in each way, and then central on the diffusive flux, and then central for the pressure gradient. Same thing for the v velocity component. So essentially, this takes care of everything in the x direction, y direction, central differencing Laplacian. So returns the sum of d to f by dx squared and d to f by dy squared. Okay, then we started setting some arbitrary numbers here. Number of points in the x direction 32, in the y direction 32. Lx, Ly equal 1, dx, dy, kind of stuff we know. New kinematic viscosity 0.05, and top velocity, wall velocity at 1 meter per second. Okay. dt is obtained from the condition on the advection diffusion equation. Although this doesn't strictly apply here, it's at least a starting point, because this equation is nonlinear. Okay, so the dynamics are going to be a little bit different than the linear equation, quite different. But as a starting point, and given this is a driven cavity, you kind of know the maximum velocity, this is a pretty good guess at your starting time step. If it doesn't work, decrease it by a little bit, and it should be just fine. But it turns out that it works pretty well. Now I created arrays for u, v, and then UH and VH. Those are U tilde and V tilde. Okay, I'm not going to use those really, but I just kind of introduce them just as if you want to store some temporary results, and then an array for the pressure. Okay, so before we get to this guy, this is what we had: a while loop, while t less than t end. Then we set the boundary conditions for the velocities. It's so easy with primitive variables to set boundary conditions, right? Especially if the boundary if there are grid points at the boundary. So you're setting the velocity directly at the boundary. Okay, you have those notebooks open? Okay. So bottom wall u and v equals 0. Top wall u and v, u is equal ut, top velocity, and v is equal to 0. Left wall and right wall, u and v also equal to 0. Now we assemble the momentum right-hand side for the u velocity. So u right-hand side is duu dx plus dvu dy. So that's ddx central uu plus ddy, pardon me, central vu plus nu times Laplacian of u. And v right-hand side is the same thing, ddx uv plus ddy vv plus nu Laplacian v. And then u tilde essentially is this is u tilde. It's un plus delta t times advection plus diffusion, right? So u right-hand side is advection plus diffusion, and v right-hand side advection plus diffusion. So u and v here, these guys, these are our provisional velocities. So if you go back to the projection algorithm, what is the projection algorithm? So let me see these steps. Let's put this one here. So this is computing this step. U tilde is un plus delta t right-hand side for the u momentum, and v tilde for the v momentum. Agreed? And we said that these velocities, so let's look at what happens with these velocities. Let's just look, say we stop here. Okay, so let's run this 4,000 time steps. Okay, it's not defined, so let me redefine these guys. Okay. Okay. Does this look like a lid-driven cavity? No. Why? Because the velocity field is not conserving mass. And indeed, as we claimed, this u tilde is not a mass-conserving velocity field. It's just weird. It just flows in one direction because it's just due to the action of viscosity, the top lid is moving at u top, and then that velocity is being diffused all the way down. But that's it. There's no mechanism for this flow to turn because we're not enforcing mass conservation. So now we need to correct this velocity with a pressure gradient. Okay, now the pressure gradient, the pressure equation was del squared p is div u tilde over delta t. Okay, so I'm going to call this whole thing the pressure right-hand side. And we have the ingredients to do it. This is where we left off last time. We said that p right-hand side is equal to the divergence of u tilde. So that's divergence u v dx dy. So what this function does is it takes du dx plus dv dy. Okay? That's what divergence is over delta t. Okay? Yes. That's the pressure right-hand side because our u now is actually u tilde. Or what we can do, we can call this actually UH and then VH, and then you can call these UH and VH. Okay? Okay, so now we need to solve for the pressure. And how do we solve for the pressure? We already did a Poisson solver with successive over-relaxation previously. You remember where we took the diagonal elements and moved everything else to the right-hand side, and we kept iterating until we converge. So it's the same thing. Okay, we don't have to implement it. Or if you want, I have it implemented here already. So essentially, it just takes the diagonal elements of the pressure and inverts them, but this is not doing a for loop. Last time we did a for loop. Turns out we can just kind of pull this out directly. It's not as efficient as the SOR, but it's a variant. It's a very simple, so there's no relaxation here. There's no over or under relaxation. But the only difference is with this pressure Poisson equations. So the pressure Poisson equation function is going to return a pressure, and it's going to take an initial value for the pressure, and it's going to return a pressure, P, and it's going to need dx, dy, and the right-hand side. Okay? Then we do some boilerplate here, and essentially we create an array that looks like P, and then copy the contents of P into Pn, set the iteration counter to 0, set an initial error to a very high number so that we don't converge in one iteration, set the tolerance, whatever you like, 10 to the minus 3, maximum iterations 50, and then as long as the number of iterations less than the maximum iterations, and as long as the error is greater than the tolerance, then solve pointwise. Okay? So what this is doing is just taking the diagonal elements, okay, and then solving for those diagonal elements and iterating. Now the catch here is that at every iteration you need to set the appropriate boundary conditions. And we said that the boundary conditions for the pressure are Newman 0 everywhere. Okay? So that's what I'm going to do. dP dy is 0 at Lx, at the right wall, at, let's say, right, at the right wall, right? And then dP dy equals 0 at y equals 0, and dP dx equals 0 at x equals 0. So what am I doing here? What kind of operator am I using? How do we set? Okay, this is a little bit confusing to you, I guess. Maybe. Okay. So this is our grid. We have a point at the boundary and a point on the interior. So let's call this, if this is pi minus 1 and this is pi. I want to set dP dx at I equals 0. So how can I accomplish this? I'm going to use a one-sided difference first order. Okay? You say pi minus 1 over delta x equals 0. So this means that pi is pi minus 1. Okay? So therefore, pi is pi minus 1. That's on the right wall. Okay? At the left wall, your indexing starts at 0. The first interior point is 1. So p at the boundary is equal to the first interior value. Same thing for y equals 0. So that's j equals 0. So p at j equals 0 is equal to the p interior. Okay, so that gives you a Newman condition. Now, we still have one wall at the top. And if we set Newman on all of them, we're not going to get a unique solution. Your pressure is going to float because you're up to an additive constant. So we need to fix one of the values for the pressure. It doesn't matter what you fix it to. You can fix it to any value you like. So I choose to fix it at the top of the driven cavity to equal to atmospheric pressure, thinking that, hey, there's wind blowing over the top, so I'm going to fix that value. Okay? So I don't want you to get really kind of stuck on this thing. We're going to revisit iterative solvers in the future if we have time. But this is no different than the SOR we did for the vorticity stream function, where we solved del squared psi equal omega minus omega. Okay? You can use that other solver as well. This is just a different way of doing it. Okay? But the point is that this solves del squared p equal b. Okay? actually, I can get rid of this guy over here. Okay. So this is the pressure Poisson. So now we are left with one step, and that is to say P is equal pressure Poisson. What do we need for the pressure Poisson? We need an old pressure or an existing pressure. So we're going to pick that up and iterate on top of it, because that's going to allow us to converge faster. From time step to time step, the pressure is going to change ever so slightly. So rather than using a 0 value for the pressure in the iterative solver, let's use the previous value. Okay? So that's going to give us the previous value, and then dx, dy. And what is the right-hand side? That's the pressure right-hand side. So that gives us a pressure. We're not entirely done yet, because we need to take now the gradient. Okay? So finally, compute the true velocities. Okay? So those velocities are going to be u n plus 1, u n plus 1 is equal to u hat, okay, minus dt times dp dx. Okay? So u, the new value that I want to put in the array u, is equal to u hat minus dt times, how do we do dp dx? d dx central of p, and then we need a dx. And same thing for v. It's vh minus dt times d dy, so that's dp dy. Okay? Clear? This is the last step in the algorithm. So after we projected, after we solved the Poisson equation for the pressure, we're going to take the pressure and put it in here. So and solve for un plus 1. Okay? You remember the algorithm. First, we solve the Navier-Stokes without the pressure, solve for the pressure, and then use this equation to get the true velocity field. So let's see what happens. Let's run this again. Yes? So we initialize the pressure here, and then we're just going to reuse it. Okay? We're just going to reuse it. Now, to make sure the boundary conditions are set on the correct velocity, actually, no, this will work. Yeah, let's run this. Okay, so we have an issue here. Tuple indices, ddx. So we made a mistake. Okay. Result. Yes. Okay. So it is telling me that it's unable to do this operation because the okay, oh yeah, I know. So this returns two values here. It returns a pressure and an error. So I'm going to do P, comma, error. Try it again. Still making an issue. Tuple object. So let me reset, because it sets P to something else. Okay, it's ran. Drum roll, what do you think is going to happen? So this was the old vector field. Let's do the new one. Okay, still posting. What? Okay. So, this is going on here. This doesn't make sense. Okay, so it looks like we don't have a pressure being solved here. Okay, so UH, we should be able to just, this is div UH, VH. So let's run this again. It's nice to make mistakes. Okay, this is still wrong. So obviously there is something going on. And I want to look at the pressure. Okay. Ah, yes, yes. Thank you. Okay, okay. Okay, so let's run this again. Thank you, Hong. Okay, so we're still having problems. What the heck is going on? Okay, the best thing to do is turn off everything. Let's see. So we get all infected by bugs. Okay, so this is still problematic. And the U right-hand side is ddxu, okay, VU, UH. So now what I'm actually going to do, I'm worried about UH. The values for UH at the boundary are not correct, I'm afraid. So what I'm going to do actually is, oh no, okay, I know the problem. This should be UH and VH. Okay, let me run this again. Okay. All right, look at that. That's your reaction. Should be like, wow. So what we did here, we took a UH and VH. So let's look at, oops, well, UH and VH is now correctly corrected because it contains some elements of U. But okay, what if I don't do this update? I just want to show you how okay, and then I'm going to plot dpdx and dpdy just to show you that the sum of the two, okay, so this is where if we plot u tilde and v tilde, this is what we get. But now we can also plot dpdx and dpdy to show you how. So if we do ddxc of p and ddxy ddyc of p, so now, look, this is the uncorrected velocity field. And then when you correct it with this pressure, okay, you get this. So let me actually show you this. So if we do the quiver again, and we do, so let's call this ddx, dp, dy. dpdx, dpdy, okay. That's dpdx. Then I claim if you do u tilde minus dt dp dx and then v tilde minus dt times dp dy. Remember, this u and v, they're actually the temporary velocity fields. Okay, minus 2p dx. Pressure plus this again. I wonder, though, if the quiver, okay, I can tell you what's going on here. The quiver would be dt dp dx and then v minus dt dp dy. Yeah, I don't know why it's doing this. It is probably in the initial, no, I don't know why it's doing this. Okay, I have to look into this, figure out why it's doing this, but it's kind of starting to look okay. The idea is as you update your provisional velocity field, you need a pressure gradient to correct that velocity field so that it is divergence free, okay? I'm gonna switch back to these guys, see what happens, why they work here. They work very well here. Oh, delta T, pardon me? No, no, it should display correctly. I don't know what's going on, but I just want to show you that they're actually, so they are different, and they should look like this, okay? And this is exactly the operation we're doing here. So I don't know why it's kind of messing up over there, okay? But this is how they should look like. I do know why. It's because you're partially right, because UH is not being properly updated with previous pressure gradients. So this is only doable for one time step. Kind of see how you can correct this. But anyway, so this is how you get it done. Okay, so you get a velocity field that looks like it's divergence free. So I'm gonna get rid of these guys. Okay. Yeah, so this is the pressure gradient. It's kind of weird. Okay. Pretty cool. So maybe we can do, let's do another case. What if we want to do, so now you can easily just switch velocity directions or add like a driven cavity at the bottom as well and play around with it the way you like, okay? Let's see, I think I had another example where I actually was trying to do a jet. I'll just show you the results from that one. Jet flow actually over a square. And yeah. So this is using the same code, but it's a different, just some different boundary conditions. But using the same code, this is the same code, DDXC, etc. Except that I have flow coming in here, and there's a little square over here, and then there's flow over the square, and then it's all exiting. And how do you do this to a very naive approximation? Every time step, I set all the velocities on and inside the square to 0. So that has the effect of zeroing all the fluxes. So nothing is going to come into the square, and then the flow is going to move around it. So that's the beauty and the power of the primitive variable formulation. And more importantly, with finite difference methods, because you have the velocities lying at the boundaries. They live on the boundary points, okay? And this is done this way, essentially. This is how I create the obstacle. I set the velocities within a range from ny over 2 minus 5 to ny over 2 plus 5, and from nx over 3, etc. So just put a square randomly somewhere, and essentially make sure that you have an inlet over here. So everything is 0 except for the inlet velocity, which is 1, and you get this. Okay? Now what is the important, this is great, interesting, and fun. So now we can do primitive variables. And then the sky is the limit here, really. I mean, we can even do complex geometries by setting grid points to 0, velocities to 0. They will look kind of jagged. So you could do flow over a cylinder, but the cylinder is going to look kind of squares with square jagged around the edges, but it's still a pretty good approximation. Okay, so, and as you refine, the effects of these, of the jaggedness is going to be reduced significantly. So just with that, going to primitive variables and using finite difference, very easy. It's very easy code, right? I mean, you'd wonder, like, why would COMSOL or Fluent, if it's so easy, why would you need thousands and hundreds of thousands of lines of code, right? Just because you want to deal with more complex situations. Over here was every time we want to change the problem, we have to redo these boundary conditions, right? So you want a mechanism to generalize that. But the core of it is pretty simple, right? And we have all the tools to do it. Now, what is the $1 million question? I'm not going to give you $1 million, probably invite you to lunch, but what's the question here? Yes, so can you explain? Okay. Yes, so what Mokbel is saying is, okay, so we claimed that this algorithm is going to produce a velocity field that is divergence-free. And from the looks of it, if we didn't correct with the pressure, everything was going in one direction. It wasn't divergence-free. But then when we added the correction for the pressure, the grad P, the flow started turning. So this means that it looks like it is somehow conserving mass. So in this case, the flow has to turn because it has nowhere to go. To conserve mass, it has to turn because the mass is going to stay in the cavity. Okay? So the fact that it's turning tells us that, yeah, very likely, we're doing something right. Okay, so let's check. It's one thing to say, to claim something. It's another to actually try it out. So let's compute the dilatation for our beautiful velocity field. And that dilatation is going to be div u. I'm going to call that div u, and that's going to be div u v dx dy. Okay? And then let's do a plt.image show just to show absolute value of div u, actually, absolute value of div u, and place the origin at the bottom. This is just a little trick because Python is going to put the upper left corner as our physical lower left corner. So you just do this origin bottom to make it look like the driven cavity. Okay, so am I going to get some votes for whether this is going to, be divergence-free and whether this is not going to be divergence-free? Why? So you got yourself into a trap now. Those who claimed it's not divergence-free are going to have to explain why. So let's see. Drum roll. Will someone do a drum roll? Ta-da! It is not divergence-free. What the hell is going on? No, that's not the significant issue here. That's not the problem. I mean, you can change the size of these vectors. This is a grid point inside the domain. That's fine. It's going to go to 0, and that's why it turns. So if you do mass conservation over here, it is turning. That's not a problem. Although, yes, the divergence looks like it's kind of concentrated over here. But still, overall, this is not divergence-free. If you go to more complex problems, you're going to see divergence all over the place. So let's understand why. Okay? We're going to go back to theory. So this method is not really used in practice. Finite difference for Navier-Stokes are not really used in practice, and we're going to explain why. But still, if you can get results with this, they're pretty darn close, because your dilatation, 7, whatever that means, div u is 7 relative to the, delta x, your grid size. Remember, your dilatation is going to go up as your delta x shrinks, right? Because you have d by dx. But it does give you the general characteristics of the flow. So you can use this to get an idea of how your flow looks like, but as long as you know that there is an error in your div u, and we can actually quantify that error. That would be an interesting problem, actually, to do. Quantify the error in div u. Okay? Now, I'm going to show you another trick. I'm going to show you something else to actually show you how I can make this divergence-free. So this is another div u calculation that I'm doing. And, this is going to work. So this is another div u, and I'm doing here, taking the divergence of UH, or U tilde, and I'm manually subtracting the Laplacian of the pressure. Now remember, what was div u n plus 1? Okay. So we said that, actually it still works. So we said that un plus 1 is u tilde minus delta t grad p. Okay? With option 1, what we just plotted, we plotted div u n plus 1. That's what we plotted. And we saw it is diverging. It's not divergence free. But there's another way to do this. And what I'm going to do is, rather than plot div u n plus 1, I'm going to plot div u tilde minus delta t del squared p. They should be equal, right? Okay. So this is div u tilde minus delta t del squared p. Drum roll. Ba-ba. 10 to the minus 15. So that's machine precision error. So it is divergence free. But how come? So this tells us that div u n plus 1 is not equal to div u tilde minus delta t del squared p. So this is what I'm going to prove to you now, that they're actually not equal. Okay? But I manually tricked the calculation to show in what sense it is divergence free. Okay? All right, so let's go back here. Boundary conditions, and then in class code, driven cavity. But this scheme doesn't work. Okay? It does not work for the following reasons. It is not divergence free all the time, as we just showed. And fixes, as we will show, will lead to what's called even-odd decoupling or checkerboarding. You've probably heard of that if you've interacted with people who do CFD. There's a checkerboarding problem. So we're going to explain, we're going to put our finger on that exactly. Who's heard of the checkerboarding problem? Yeah. Okay, do you know kind of in what context? I guess with the Uinta team? Okay. Unphysical solutions in the pressure can be admitted by this scheme. That's also called pressure checkerboarding. Unphysical solutions in the velocity can be admitted by this scheme. That's called velocity checkerboarding. We're going to talk about something really, really complicated called the div stability condition. So finite difference with Navier-Stokes does not work for all of these reasons. Okay, and we're going to go over each one of them briefly. First, let's start with the elephant in the room. It's not divergence free because we just kind of saw how that it's actually not. Div u n plus 1 should be divergence free, at least to the grid definition that we use for divergence and gradient, right? Okay, so it's not divergence free. So let's check if our updated velocity is truly divergence free. So I'm going to take the divergence of u n plus 1 is div u tilde n plus 1. But I'm going to do something here. Rather than say div grad is equal del squared, I'm going to keep it div grad p in this form. I'm going to keep it in this form. Okay? But we are solving del squared p equal this guy. Okay, so this is a given for us. So therefore, div u n plus 1 is equal to 0 if and only if this guy is equal to that guy. If div grad p is actually equal to del squared p. Now you can immediately tell, because we are using central scheme for gradient and central for divergence, that div grad is not equal to del squared. It's actually going to produce a much wider stencil. So let's see what this means. So let's check. This is a grid with pressures on it. Okay, del squared p, this is at least how we define it. We just use a central scheme for del squared p. So for point I, it's pi plus 1 minus 2pi plus pi minus 1 over delta x squared. Great. Now what is div grad? So div grad is div of grad. So that's grad pi plus 1 minus grad p at I minus 1, right? So div grad p at this point at I is grad pi plus 1 minus grad pi minus 1 over 2 delta x. Now what is grad pi plus 1? It's pi plus 2 minus pi over 2 delta x, right? And same thing for pi minus 1 is pi minus 2 over 2 delta x. So that gives you that div grad p is pi plus 2 minus 2 pi plus pi minus 2. Look at how we ripped apart the stencil. So in reality, del squared p is not equal to div grad p. And that's why the pressure that we obtain from this guy, according to this operator, is not going to return the same value when we put it in div grad. Because because the effect of div grad is to untangle the points versus returning this same thing. Is this clear? So what we did by so the trick I did here was force div grad to be equal to del squared. So that's why when we do this, you get divergence free. But it's only a trick. That's not. The reality is that this needs to be divergence free. Div un plus 1 needs to be divergence free. But it's not, because div grad is not equal to del squared. This whole thing, the Helmholtz decomposition, works if and only if div grad equals to del squared. So you will hear people from the finite element community or unstructured grid community, they talk about the div grad problem. That's it. That's the div grad problem. Okay, and we are trying to be consistent. So we use second order for, pardon me, for gradient, second order for divergence. Okay, and once we combine them together, everything blows up. Okay, so then you could say, you could argue, okay, why don't we make this guy equal to that guy? Why don't we make del squared actually equal to div grad? So rather than solving pi plus 1 and pi minus 1, let's just do pi plus 2. Okay? So you can make this argument. We call this a wide stencil. So let's do this. So this actually leads to our first checkerboarding problem called even odd decoupling. So let me explain to you what happens. So assume you are solving. So this is a grid, periodic domain. And in the red points here, I'm putting the periodic points. So P1 and Pn need to be equal. So therefore, this guy is this should be P2 and this is P3, okay, because these are periodic points. And this guy is Pn minus 1, Pn minus 2. There's a typo here. Okay, let me correct that since I'm at it. So we said this is Pn minus 1, right? And this is Pn minus 2. And this is P2. And this is P3. Okay? Okay. What? No, this is P1, this is P2, and P3. Yeah. Okay. So now, I'm just going to give this example. Say I want to solve this equation, d2p by dx squared equal 4 pi squared sine 2 pi x. That's going to call this b. And I'm going to use the wide stencil. Okay? I'm going to use the wide stencil. And of course, it is not working. Okay. So with the wide stencil, then at point 1, we have P3 minus Pn minus 2, P1 plus Pn minus 2. So remember, we're doing a wide stencil. So at P1, rather than using the neighboring points, we're using the outside neighbors, okay, the wider points. So for P1, we're going to use P3 and Pn minus 2, okay? It's for delta x squared B1. And then for P2, and then for P3, all the way to the end, to Pn minus 1, which is going to include P2 and Pn minus 3, right? So Pn minus 1 is going to include P2 and Pn minus 3. And for Pn, we're going to include P3 and Pn minus 2, okay? So in the interest of time, I'm just going to show you the results. So this results in a coefficient in a system of equations that looks like this. It's a very it's a sparse system, okay? But the diagonals are, there's a zero diagonal here and zero diagonal here, right? Because we are skipping every other point, okay? So when you solve this, this is what you get. The exact solution is in orange. But then you get, so when you plot it, actually, it looks like you have oscillations, right? But if you don't draw the lines between the points, it looks like that you're actually getting two solutions. And that's what you're getting. You're getting, actually, you're solving two independent systems of equations. The odd points are all coupled together, and the even points are all coupled together. So let's show how this works. So if you take this coefficient matrix and just rearrange the rows so that the odd numbers, so P1, P3, P5, P7 are next to each other, and then P2, P4, P6, P8 are next to each other, this is what you get. You get the first system of equations and then the second system of equations. And they're only coupled by these points. So there's very loose coupling between these two systems of equations. So you're really taking the mesh. If it were not for the periodicity, you just completely rip the problem apart. So in other words, you are solving two systems of equations. And in practice, that is going to lead to oscillations, like I showed. So if you use the wide stencil to solve for the pressure, you're going to get all sorts of weird behavior, okay? And we don't want that. So that's a problem. Okay, so we cannot make del squared P equal to the wide stencil. Maybe in some cases it may work with certain boundary conditions, but in general, you don't want this phenomenon to occur. And you're actually decoupling everything. But that's not the entire story. There is another problem as well. And give me a second, please. Apparently my slides did not sync properly with the animations that I was doing. Okay. That is one of the solutions, but doing that is going to be, you're wasting a lot of cost. In 3D, that is going to be extremely expensive. But in essence, what you're talking about is the staggered grid, in which this is going to be the remedy. So we're going to, rather than placing all the variables at the same grid points, we're going to place them at intermediate points. So we create a fictitious grid that is a little bit off, as if you are doubling the grid points, essentially. Okay, let me just... For some reason, I am unable to add an effect for these equations. Okay, so pressure checkerboarding. Okay, consider the following 1D situations. Forget about the equations. My animations, it's not allowing me to change the animations for some reason. Okay, forget about these equations. Now let's look at this grid. Consider the following situation. It could arise from an initial condition artificially or during the solution. In practice, it may never happen, but an algorithm that you can poke holes in it is not a good, a lot of holes in it is not a good algorithm. Okay. So consider the following situation, and it's not absurd to initialize your velocity with a constant everywhere. So imagine it's 1 or 10 or 7, whatever, at all grid points. And also imagine somehow your pressure is oscillatory in this sense. It's 2, 1, 2, 1, 2, 1, 2, 1. Could be whatever value, as long as every other point is the same. So these points are equal in pressure, and these points are equal in pressure. Now, physically, a pressure field like this is extremely oscillatory. And this kind of pressure field should create insane flow, okay? This is like turbulent mixing, crazy flow. A pressure that looks like this, okay? Yet, if you plug this, if you try to do the calculation with these numbers, this pressure field is not going to be felt by the Navier-Stokes equations. So let's show how. Because the velocity is constant, all the fluxes are 0. duu is 0 and d2u is 0. right? That's kind of the initial step. Now, the only way this velocity is going to change is from the pressure gradient. So you go calculate the pressure gradient. It is 0, right? Because at this point, it's 2 minus 2 over 2 delta x, 0. At this point, it's 1 minus 1 over 2 delta x, it's 0. So every grid point, so grid points do not sense the presence of a pressure gradient, although your pressure gradient is insane. You have oscillations, right? There's a highly oscillatory pressure, but it's not being sensed in the pressure gradient. So what this means, if you plug the numbers, what this means is that your velocity is going to remain the same at all times. Un plus 1 is always going to be equal to un because there's no pressure gradient. Even after you solve the Poisson equation, all of this, it's all going to be 0. It's not going to make any difference, okay? So in other words, despite the fact that there's a highly oscillatory pressure field, your Navier-Stokes equations are not going to sense it. And that is the pressure checkerboarding problem. It shows up on finite difference, and also we're going to show it shows up on finite volume collocated schemes. Anytime there's a central discretization that skips a point in the middle, you're going to get this. Now you can argue, why don't we do forward and backward differencing? First of all, you're going to drop order. Secondly, they may not always work because you're going to hit other stability issues. And maybe you don't want first order on momentum. Okay, so in principle, you could say I can do first order on forward for the gradients and backward differencing for the velocity, but then backward differencing for the velocity. What if the velocity is going in the opposite direction? That is going to cause, so backward difference on the velocity is like an upwind scheme. Okay, but it's not really upwind because if it's always backward, then your velocity is going to be in the other direction. And it's going to cause instability. Then you could say, oh, we can condition. If we were doing backward on the velocity, we're going to do forward for the pressure. It messes everything up. It doesn't work. Okay? Velocity checkerboarding. Consider the following 1D situation where the velocity is highly oscillatory. Okay? So now we're starting with a highly oscillatory velocity or an initial condition. Say you're doing turbulence and you just kind of randomize and you hit this kind of initial condition. So you'd expect that a velocity field like this is actually going to induce pressure changes, okay? And those pressure changes are going to cause motion, etc. So what happens really is this velocity field is actually going to create a 0 right-hand side for the momentum. So in other words, u tilde is going to be equal to u. And when u tilde is equal to u, then your Poisson equation gives you 0. With Newman conditions, it gives you a constant pressure. So there's no way for this highly oscillatory velocity field to cause pressure changes. Okay, so it's going to cause the opposite problem that we saw earlier. Despite the fact that we have a highly oscillatory velocity field, your pressure is always constant. So you can run the numbers by hand. And finally, the most misunderstood and possibly undiscussed condition among the CFD world, and that's called the diff stability condition, or the Ladijenskaya-Babushka-Bredzi, LBB condition. It's a theorem in finite element analysis, kind of hidden in the middle of nowhere. You can see it on Wikipedia. You cannot follow it. I don't even know how it works. I just take the results from that theorem. And essentially says that the combination of centered finite difference schemes and collocated grids, so in other words, putting all the variables at the same point, plus centered finite difference schemes, does not satisfy this diff stability condition. And the diff stability condition is a condition necessary for the convergence of numerical schemes of the Navier-Stokes equations. Okay, so this combination, if you don't satisfy the diff stability condition, your code doesn't work. It is necessary to use different meshes and or different order interpolants for velocity and pressure. So we saw that if we use the same order for div and grad, it messes things up because everything is collocated. So the solution is either to use different interpolants forward and backward, but we just kind of discussed that's really annoying and hard, or use different meshes like Aaron was saying. And that leads us to the staggered grid for those who know what the staggered grid means. This is kind of the rationalization for it. Or one other way to fix this is to modify the continuity equation. And there's a method called the method of artificial compressibility that modifies the continuity equation so that even if you're using finite differences with cell-centered schemes, you don't worry about this grad P anymore. You're not doing a projection anymore. And so you can converge the system. We may discuss this a little bit, but it's not a very popular method. Okay, it's more of a fun and interesting exploration. Okay, so what is the remedy? We're gonna do actually this point. We're gonna deal with this point. We're gonna use both different meshes or different order interpolants. Okay, so we're gonna discuss those. So the remedy is the staggered grid. The first remedy, the first step to get to the solution is to use the staggered grid. I'm going to give you a simple motivating 1D example, okay? And the idea of the staggered grid is to place velocities and pressures at different points on the grid, okay? So rather than putting the grid points, putting all the variables at the same grid point, we're going to place them at different locations. Now, we're going to place the pressure. If this is your computational domain, if this were your boundary, we're not going to put a point at the boundary. We're going to put a point in the center between the boundary and the next point, and then delta x, delta x, delta x. So there's a delta x over 2 here, and then delta x all the way, and then delta x over 2 over here at the end. And we're going to place the pressures over here, but we're going to place the velocities over there. We're going to stagger the entire grid. So if you think of this as your grid, we're just going to shift it to the left by delta x over 2. And we're going to use that other grid as a placeholder for our velocities. And the indexing, by convention, goes like this. This velocity has the same index as this pressure. Okay? And this velocity has the same index as this pressure, and so on. Okay? So we're still doing finite difference. Now, the equations that we want to solve, I'm going to give the example in 1D just to help you fix the ideas in your mind. We're solving continuity, du dx equals 0. Of course, that's going to give us u equal constant, for sure. And momentum equation in 1D. So you just have one convective flux and one diffusive flux, and dp by dx. Okay? So let's go ahead and discretize those terms. Now, I change the nomenclature. Pi and ui, pi minus 1, ui minus 1, pi plus 1, and ui plus 1. Now for my derivatives, now this is going to create an interesting problem because now different variables live at different locations. But if you're integrating the momentum equation, you want to integrate everything at the same location. So all the terms on the right-hand side of ui need to be computed at this point here. Okay? So what I'm going to introduce, the notation I'm going to introduce is, say, the first term on the right-hand side of the momentum equations, duu, du by dx, I want to compute it at ui. So that's what this nomenclature says. If I put at I, what is I? Is it pi or ui? Okay? So you agree that everything on the right-hand side of the momentum equations needs to be computed at the same location of that momentum equation. So all the right-hand side terms of ui need to be computed at this point here. So therefore, I'm writing duu by dx at ui. So I'm just going to take a simple central differencing. So that's ui plus 1, so this guy, minus that guy, over 2 delta x. I really like doing this because it kind of central differencing, that's what it does. It takes two values, moves them to the center. So we're taking those two values and computing a value over here. Same thing, duu at ui plus 1 is these two guys over here. Okay? Great, so that gives us the advective term. Now, the diffusion term, d2u by dx squared at ui, That's, again, ui minus 1 minus 2 ui plus 1. And it lives here. Okay, it lives here. So those are the terms on the right-hand side of the u momentum equation. Next is dp by dx. This is where the interesting stuff starts coming in. dp by dx at ui, what do? We just say pi minus 1 over delta x, right? Now, what does this look like? No, it looks like a backward difference. So we are tricking our equations to use, just by moving variables around, we are tricking our equations to think that we are doing combined interpolants. It looks like a backward difference from the perspective of pi. And from the perspective of pi, it is a first-order approximation. But from the perspective of ui, this is a second-order approximation, because it is over 2 delta x over 2. So from the perspective of ui, this is a second-order approximation. See the brilliance of this. This is the MAC method developed at Los Alamos, Marker and Cell. So this is the leftover of the MAC method. OK, so now u tilde at I is u at I, un at I, minus delta t advective term plus delta t diffusion term. Okay. Now the projection. Remember, we had a del squared p equal 1 over delta t div u. But where are we evaluating del squared p? At pi, right? Because that's an equation for the pressure. So del squared p at pi is equal to div u tilde at pi. Okay. So what does this mean? Del squared p is the same, pi plus 1 minus 2 pi plus pi minus 1. But what is div u tilde? Remember, we have a u tilde here and a u tilde there. And we're evaluating div u tilde at this point. So it's simply u tilde I plus 1 minus u tilde I over delta x. What does this look like? It looks like a forward difference. But it is second order with respect to the pressure. It is first order with respect to the velocity. See how brilliant this is? Okay. Now we claim that then when you do the update, ui at n plus 1 is ui minus delta t dp by dx, where evaluated where at ui. If you follow the nomenclature here, it can be confusing. Think about it on the grid. Say, OK, dp dx, if I'm computing the pressure gradient here, it's just simply taking these two values and doing the pressure gradient. OK, so let's check if this is actually divergence-free. Okay? So to check if we're divergence-free, we want to take div u n plus 1. But where are we evaluating the dilatation? At the cell centers. Okay, because the dilatation is consistent with the pressure equation. So it needs to be evaluated at the cell centers. Or in other words, dilatations actually take things, or dilatation is going to take velocities and move them to the cell center. Okay? So that's why I say du by dx at pi. Okay? So that's equal du tilde by dx at pi minus delta t. Now this is a funny one. Delta t div grad. Okay, so this is div grad. This is d dx of the pressure gradient, but evaluated at pi. Now remember, the pressure gradient lives here, right? Because when we computed the momentum equation, the pressure gradient, we took these two p's and put them here, and these two p's and put them here. So we have a pressure gradient here and a pressure gradient there. And then we're going to take its divergence to put it here. Makes sense? So the one on the inside is going to move p and put it here, and move p's and put them here to create a pressure gradient. And then the outer derivative, which is the divergence, is going to take those gradients and put them back in here. So you go ahead and do the math. First term, easy, du tilde by dx at pi. So that's u tilde at I plus 1 minus u tilde at I over delta x. Minus delta t, we said this is div of grad p. So that's essentially grad p at ui plus 1 minus grad p at ui. Grad p at ui plus 1 minus grad p at ui. Again, a forward difference. Okay. Then this guy
is pi plus 1 minus pi over delta x, and pi minus 1 over delta x. And you see how I'm getting excited over here. And that's actually equal to the del squared. So div grad is equal to del squared just by moving things around. And that is the power of the staggered grid. That's why we do the staggered grid. It discretely satisfies the continuity equation. But programming this is a nightmare, and we're going to program it together, okay? And we're going to see how annoying it is. And then we're going to come up with a way to not move things to stagger things. We're going to do them all collocated. But like Tim kind of jumped the gun, this leads us actually to the finite volume method, okay, which we're going to begin on Thursday. Okay, we're going to start discussing finite volume methods, but we're going to go back to the advection diffusion equation to just get some mileage with finite volume methods. And then we'll go back to the staggered grid and show how the finite volume method leads naturally to the staggered grid, okay? Okay, I hope this was exciting and interesting. Kind of finally, you know, you hear all of these things. I personally used to hear all of these things from my teacher. Oh, this doesn't work, that doesn't work, but I had no idea why. And so I think it's interesting to kind of look back and see why these things don't work. Okay, thank you very much.